relational database basics is what we're going to talk about in this afternoon. And you're here, so presumably you have an idea of what you might want to do with databases, but maybe you're just curious. And so, just as an introduction, it's always good when your binary data is nicely pixelated. It's extra binary, I find. Is the idea that we have a lot of data these days, and they come in all kinds of forms. Some comes in just binary by default. Some comes in as text. Some comes in as structured text. Some comes in as unstructured text. And then there are databases. So databases are a way to store your data. And so I looked up what a database supposedly is by definition, just to go, okay, how general should I make this? Well, if I take the literal definition, it's an organized collection of data for storing, managing, and retrieving information. Then that is almost anything that deals with data, except for those people that just dump data on a drive and don't organize it. But that data is now random and isn't data anymore. But what it really, people mean something else with it. They mean a very structured way of dealing with data. Usually, these kind of databases have applications in like websites and things like that, where you have to store records of people or transactions or banking information, stuff like that. What doesn't necessarily define them, but in practice does show, just dictate what they look like, is that our structures as tables. So they consist of tables with tables with tables with tables. And that seems very restrictive, and it is in a sense. You might think that your data is not a table. It's not a two-dimensional data. It's something else. But the idea is that when you have a table, you have rows and columns, and you could think of every row as a set of column values. So every row is a relation between the values in those columns. That's actually why it's called a relational database. Even a single table is already a relation between data, namely the data in each of the columns of a row. And if you think of it as a relation between those things, then unless your data is completely unrelated to each other, you would have some relations. So thinking of how, even if you don't really have tabular data, how your data might fit in a database can give you a better handle on structuring your data in the first place. If you have several tables, you'd often want them to refer to one another. Like one entry in one table might refer to an entry in another table. So those, again, are relations that you can do. And you'll need to have some way to identify that row over here points to row over there in the other table. You do that through keys. So that's another way to have relations. So you have relations in a table and between tables. And a second, or a last, not so much defining, but practical aspect of using databases is that they come with a standardized way to access them called SQL. So that's Structured Query Language. This is a more or less standardized language by which you can access these tables. And here it really helps that everything is a table, because the data structure is so stringent. You can have a language that is standardized. If it was more complex, then you'd never find people to agree on how to do this. So we will see that this SQL language, this SQL, is almost always used from another host language. So it's sort of an embedded language that you use to talk to a database, but you talk to the database from some other program, like a Python script. So we're going to look at Python specifically. We're going to see how in Python we can make an SQL query and give that to the database and then get results out. So it's sort of the lingua franca between your favorite programming language and the database itself. You don't have to do this in Python. You can do it in any language. So if you want to do it in R, if you want to do it in C, yes, you can. Right? It's just a different way of calling these things, a different interface, a different library to do that. But the language that you use to access the databases are the same. So that's more of a practical definition. Tables with relations between one another and a standard language to manipulate and retrieve things from those. And so that's what we're going to look at today. Now, again, you might think, well, why would you do this on a supercomputer? It sounds very heavy-handed, very restrictive. And in a lot of cases, you don't need it, not to compute things on a supercomputer like the ones we have. But maybe your application just wants one, right? That's not common. It needs to store some data. The application's developers have decided to use a database. You need it. So, OK. It is more structured than using a file system, which can be good and bad. Usually it's good. The file system lends itself to storing your files in directories in some hierarchical way. But because it's so general, it's very hard to optimize the access to that. So you want to go 5 directories deep and list 10,000 files, and it's going to take a little while. There's no way that the file system knows that that is what you're doing. And the databases have a little bit more smartness to them. Another thing that is nice about databases, rather than just putting files, is that it's a bit more self-documenting. It's clear what belongs together, what points to what. The relations are more obvious. So that's nice. And because it's restrictive, I already said that, it's kind of easy to efficiently get data. It still depends on the database and the implementation of that database, obviously. But there's not much that can get in the way. You want these rows, and you just get those rows. If you want 1,000 rows, you could do that in parallel. I don't know if the database will do it, but there's nothing standing in its way. Just a little example here of how you might retrieve some information from that database. This is a bit of SQL. Select star from measurements, join parameters where pressure is less than 2 and n is less than 50,000. This is to show that this is a fairly verbose language. What it means is that it selects all columns from 2 tables. One is called measurement, and the other is called parameters. And it joins them together as one big table. And it only selects those where the pressure is less than 2 and the n, which stands for number of particles, is less than 50,000. So it's fairly expressive, and you can make these very, very complex. You give this expression to the database, and the database tries to figure out the most effective way to retrieve these things. In this case, there might not be too much to do, but maybe it could first select in the measurements if the pressures are less than 2 before joining. There are things that it could try to do to make things as efficient as possible. So this is what it's going to look like, and it will give those records back. Just so you know, you'll see these kind of abbreviations like RDBMS. Just means Relational Database Management System, and for all intended purposes, they're the same as just relational databases. Yes? Yeah. So what I'm going to try and do, because we are SciNet and we host supercomputers, is I'm trying to see how our users might use databases. So if you have a website and you use it, yes, there's no question why you should use it. But if you're doing computations and you're doing large fluid dynamics and you just have a bunch of simulations to do, or you're doing molecular dynamics simulation, you're going, nowhere in there do I need to store my atoms in a database. Like, what is the point? And so I'm just going to store it in files. So this is to show that yes, that's true, you can do that. But this might be a more structured way to do it. Mm-hmm. No, supercomputers is just basically anything that is, let's say, anything that computes in a non-interactive way. Like that, I mean, that's if it gets multiple users, and you're using it mainly for compute, not just to do like word processing, that's super enough. Yeah, yeah. Oh, yeah. Oh, yeah. Yeah, yeah. Yeah, this all translates. It's motivated from, okay, how would you use it on a supercomputer? But that could be a 3-node supercomputer. It could still work. It's more the fact that you need a lot of data that you want to store than how you're actually working with the data. So there's also cases where you might not want to use relational databases to store your data. Actually, there's many of them. So you can store anything in a database. You can store binary data in it, sure, but but you would do that in a way that you don't give any structure to that binary data. It's just a blob. It's actually called a blob of data. That's not useful to anybody. There are better formats for binary data. So if there's NetCDF, HDF5, if you have some grid data, say you're doing a simulation of the atmosphere, and you want to know, the temperature, pressure all across there, you're not going to store that in a database. It would be inefficient. There's better ways. So in many cases, sort of binary data, so your raw grid-based data or anything numerics, you might not store in a database. But you could store things about the data in a database, right? What else? Yeah. There might be a bottleneck. If you have a single database server, then yes, it might be powerful, but it still has to do every query one at a time. One thing that we're not going to focus too much about, but which is true, is that a database always maintains its integrity. So if I change a table by adding, say, a row, it always adds the whole row as one. So there's never a case that some other application that's also trying to access that database sees a half row. In other words, it's always consistent. That's great, but that means that when one process is updating your database, the other process has to just wait until that's done. And so that can lead to bottlenecks. Whereas if you're just writing, if each process is writing its own file, and especially if you have a parallel file system, like on SciNet, it just goes. They don't have to wait for another. So there are cases where it could be a bottleneck. And as I said, it cannot do parallel I/O in the same sort of way. It can't generate data or ingest data in a parallel fashion. It can retrieve them somewhat in parallel if the database is clever enough, but the access has to be one by one. So it's not good for everything, and that's okay. There's no reason to not combine databases with the sort of traditional approaches. You just leave your binary data in your favorite, hopefully documented binary format, and store all the things like how you got that data, so what we would call metadata, how you run your simulations, how long it took, where the locations are of your files, so basically the different cases. You could store those in the database, and that could be useful, and actually probably lends itself well to having tables. It's kind of like a log book, right? Like a lab book where you keep a log of all the things you're doing. It would have lots of tables, but your actual data might be somewhere else. So we're going to look at a use case that sort of reflects how you might do this combination of raw data and a database at the same time. And we're going to look at what's called a parameter sweep. So parameter sweep is when you have a case to compute, and you have to do the same kind of computation, but with different parameters. So here's an example. So my background is in physics and chemical physics, and I used to do a lot of molecular dynamics simulations, and this use case reflects that. So here's a bunch of balls, green balls in a box, but we're going to pretend that these green balls are actually argon atoms, and that this is a gas, an argon gas or argon fluid. And what we want to do is we want to see how, as a function of the pressure in the box and the temperature in the box, we want the pressure as a function of the temperature of the box and the density in the box, so the number of particles we put in this box. And we want to do this basically for general case. We want to vary the pressure, vary the temperature, vary the density, and get the pressure. It's called a phase diagram or a phase function that we're trying to do. And how we're going to do that? So we're going to try and basically create a grid of temperatures and density values that we are interested in, some physical parameters, a square basically. And then for every point in that grid, we're going to do a simulation, and the simulation will tell us what the pressure is, and that'll be the end of it. This has been done. This is not new stuff, so this isn't cutting-edge science, but doing something like this is very common. You might want to know how a protein folds, how a certain mineral gets through your pores in your cells. Something like that might require a lot of different cases to try, and you could run them in parallel, but you still have to sort of keep track of all these cases that you've done. That's what we're going to do. So we're going to use an application that was given to us. It can do the simulation. That we don't have to do that. It can be fed different input parameters through configuration files or command line arguments, and then we have to keep track of what we've done. So we imagine it's so simple that you could actually just do it in a few minutes on your laptop, but we're going to imagine that this took a lot of time, that we're requesting that time in batch jobs on the supercomputer, that we have to wait a few hours for these to run, but we have thousands to do. So we need some way of sort of keeping track of what's done and what's not done yet. The jobs, the parameters, the results, and where they are. A few more things just to give this use case a bit of explanation. What the simulation does really is it takes a given number of atoms, it places them randomly, and then it starts computing how they would move as they feel forces that act between them. The force is that is appropriate for argon atoms, at least to a good approximation. And then it's going to average along the motion what the pressure is and give us that. So we can have different size boxes. If we make the box smaller with the same number of particles, it's a higher density. So we can get different densities by having different box sizes, and that's what it does. Another thing that happens, and that's just typical for molecular dynamics simulations, is that when you start your particles randomly, that's not a very natural state for this gas. So it actually will compute the motion, and they will find their equilibrium, more or less. So you wait a little longer before you actually start taking the average. A way to get, so the density gets set by the size of the box and the number of particles in it. The temperature gets set by the average velocity of the particles. So that's set initially as well. And so that's how you get the temperatures. And then just so the output of this program doesn't hold any surprises, time is measured in picoseconds. So we're going to really be computing very, very short real times. And the lengths will be in angstroms, which are 10 to the minus 10 meters. Temperature will be measured in Kelvin. Energy is going to be kilojoule per mole. And density is going to be mole per liter. You can see the chemistry in this application. And the pressure will be in megapascals. Okay. It doesn't really matter. It's just so you know that this is what is output. Okay. So you can either follow along or just believe what I say. But if you want to follow along on Niagara, you can log in. You use SSH with your username at niagara.scinet.eurocontrol.ca. And then there's a Git repo at /SciNet/courses/dbb19 for database basics 2019, which you can clone and then CD into it. And then there's a couple of modules that you will need to load to make everything work. They're all in a script. So if you source the setup script in the directory, it will basically just load the modules you need, and then you can make the application. The application that it builds is called LJ. And then maybe we should do it live in a second. And then we can run simulations by basically saying the name of the program. We give it a label that is also the name of the directory that it's going to store stuff in. The kind of atom we want to compute, it can do more than argon. We're just going to do argon. And then the temperature, the density, the number of atoms, how long we want to simulate for in picoseconds, the time step. So it's a very short time step, but we have to do that. And some random seed. The random seed determines how the positions are initially. What it will, if you run it, what it will produce is just an output file, output of that. I've stripped out, it used to also dump out the trajectory of the molecules, and that just gave everybody a whole bunch of big files, and we are not going to do anything, so I stripped those out. This is just reporting the averages of the energy, the temperature, and the pressure, which is what we will need here. Just making sure that this works. Which one shall we do? Where's my terminal? Somewhere. Okay. Yeah. Okay, so I've that's right. So if you look at the output, so I've done this once. So this is the content of that. So if you look at first run, and you look at output, there's actually there is a header. So the first column is time, the second column is energy. This is the potential energy and the kinetic energy. So energy due to motion, energy due to the forces, and then the last two are the temperature and the pressure. Okay. So the density we would have to compute from the number of particles and this. Wait, where's the density? We have a density. So a number of particles. Oh, and from the length. But I think we set it on the command line. So this is exact. Oh. Okay. So I ran exactly this command. So the density will be 2.5 mole per liter, and that would correspond to n divided by the cube of this L. L is the length of it. And so it goes in time. It skipped 6 picoseconds. That's that burn-in time that I was talking about before it takes averages. So it doesn't really show those. And then towards the end, so it does that for a whole bunch of time steps, keeps the average, but doesn't print the averages. And at the end, it does an average. So this last column has again the label, the name of the substance, and then the averages of the columns. So average energy, average potential, average kinetic, average temperature, and average pressure. And of course, in this case, that last line is all we really need. We're not going to do more with the trajectories or with the fields, but that's just to keep it simple. Yes. Yeah. Well, it is for a reason, because what happens is that this is a fixed box and a fixed temperature. So the pressure is really how much is it kicking against the edges. And so sometimes there's more particles kicking the edges, and sometimes there's less. So that's why it fluctuates. And the bigger the system would be, the less it would fluctuate, because on average, it's always the same amount. So yeah, it's very typical of doing particle-based simulations. With low number of particles, everything will fluctuate. Everything around a set average, but that's it. That's why we have to simulate it for. Okay, so that's what we're going to deal with, and yeah. So yeah, it already says the last line is for us here the important one. So our script will just extract that last line, and put it in some sort of database. So that's what we have in mind. And this grid that we will choose won't be very big. But you can imagine that you want like 1,000 by 1,000 points. That's 1,000,000 runs to do, even if they don't take much time. That's still quite a bit of stuff to keep track of. You could try and make 1,000,000 directories, and then our file system will say, no, I don't like that. Go away. So you need a way around that. So that's the use case, and we'll come back to that. Let's look a little bit at the particular database that we are going to use. And by the way, let's see, just ahead of time, let's say that we take a break at 2:30. If I don't stop at 2:30, just stop me for you. It'll take a little, bathroom, coffee, break, 50 minutes before I forget. Okay, so let's look at there's a specific database that we are going to use. There's lots of different ones, but we're going to look at SQLite for a very specific reason. So here's a few relational database management systems, so RD, MBS, or something, SB, that are out there. There's lots of commercial ones. Oracle, IBM, Microsoft, SAP, they all make one that you can pay for and trust and get support for. There's also open source ones that you could deploy yourself at no cost. And some of the more popular ones are Postgres and MySQL or MariaDB. SQLite is also open source and also free. We're choosing that because it comes with Python, because it's simple, But there are a few restrictions. Like it's not as full-fledged as the other ones, but it is very good to get started with and to learn a little bit of SQL and how you interface with Python. So everything we will use fits within that scheme. Another really nice thing about SQLite, it's open source, it's light, it's relatively simple, is that it's serverless. So you don't have to set up a database server, and not even on the same machine. The file is the database. And that actually works really nicely in a distributed supercomputer like ours, where you're going to submit these jobs, right? These compute jobs, they all run independently on their own node. Once they're done, you don't have anything running on the system. That's how supercomputers tend to run. You log in, you submit a job, you log out. At some point, it runs, and that's it. That means that you don't have a job running that runs the database. If you needed a server, that can be complicated. Now, it's not that you couldn't come up with sort of a job that's always running and that plays the role of that server, but it complicates things a lot. If your server is a file, well, the file is always there. You've solved that issue. So it's actually kind of a nice fit. So it's a file. There's a command line interface with it, SQLite 3, where we can type in SQL directly. We'll try it out a few times. It comes standard with Python. We're going to use Python 3 in the examples, but I think everything works in 2 as well. But that's nice. If you've installed Python, you can do import SQLite 3, and you will have an interface to SQLite. There's interfaces for C, PHP, Perl, R, and what have you. There's also some third-party GUI interfaces, so things that don't come with SQLite or with Python, like SQLite Browser, which we also have installed on Niagara, and which can be nice ways to sort of browse through your database. Yeah. Yes. Right. No, I like pandas. It's great. The only downside with pandas, and you only get it when your data is really big, is that it will try and read in the whole database at once. And so when it fits in memory, pandas is fantastic. When it's not, you might want to do. Now, you could just read in a part of the table. It's not that you can't do that. So, but then yeah, I like Python, so it'll work. But yeah, just read it in, and now you have your table in pandas. That's great. Now, of course, now you want to write back to it. So we're going to not do pandas today for that reason. It's just extra complications. But yeah, no, it interfaces very nicely with it. Okay, so a few things that are different between the different database management systems is what data types that they support. And here's where SQLite shows its lightness. It only has 5 storage classes. Others have way more. One is actually not a storage at all. It's nothing. It's called null. You can store integers, so whole numbers, real, so floating point numbers, text, and then blob. Now, blob is any binary data. You could store anything in it. Don't put binary data in there, though. You could. It's sort of a patch, but you can. So that means you can store anything. But for many cases, integers, floating points, and text are pretty much what you need. Other SQL types that are very common, like tiny ints, which take less bytes, a variable char, so that's not a text that can be arbitrarily long. A date, so in SQLite, a date is just a string with a date in it. In other databases, that has its own format, so that it's always formatted properly, etc. Now, SQLite will sort of accept these sort of types as a declaration, but it'll just basically map them back to one of these. So date becomes a text, tiny int becomes just an integer, varchar just becomes text, and that's just the nature of this beast. Okay. They call it having affinity with another storage class. Yeah. Good point, and the answer is not really. So when you have to store arrays, you either figure out that they're not arrays, or you're going to store them outside and just put a pointer to, hey, that's the file where they're in. There are extensions to databases where they do store arrays. but they haven't gotten much traction because in the end of the day, you might as well store it in HDF5 or netcdf or something like that, which does that well, and then have the name of that binary file as a field in your that's yeah. Okay, so apart from our use case of these molecular dynamics simulations, I also have just some simple examples because well, because there's cats and dogs and they have to be in a table. So let's look at how SQLite works in Python, just a simple example. So suppose we have a table of our pets. We have 2 cats, we have 2 dogs. Their names are Missy, Puppy, Bingo, and Kitty. And some of them are cats and some of them are dog. That's a relation between their names and their type. And so here's a relational database. It's a table. It has 2 columns, 4 rows. Say we wanted to put that in a database in Python, then this would be the sequence of commands that we would put in. So we'd start with importing SQLite 3. That is the interface package that gives you SQLite. It is version 3 of SQLite, but that's okay. That's where we're at. The first thing you want to do is usually is to connect to a database. Now, if this were a server, this would be actually a connection. It would just go over the network and try and get a handle. In this case, we just give it a file name. It could be in some directory, so in some directory path. There's a file name .SQLite3. And the connect, since this is a database that didn't exist yet, just creates that file. In the case of SQLite, it is that simple. The database is the file. So the connect is just creating a file or opening a file for reading and writing. And then we want to do something with that, at first, empty database. And we want to create a table. And so we need to say db execute create table pets, name text, type text. And then after that, we can insert values into it. So we insert values into that table, pets, the values Missy and cat. That's number 1. Puppy and dog, Bingo and dog, and Kitty and cat. I tell the database to execute these, but actually I have to say that I'm really sure that I want to do this by doing a commit. And then after the commit, this is stored. I can go and get that table back. So I can do a select everything from pets. So star means everything here. And then fetch all of them and then close them. I'll go through each of these statements, exact syntax, and why they look like this. But that's what it looks like. It's Python, but there's some strings with SQL in it. So the outer part, this execute part, that's Python. That's just a function in Python. So db is a Python object. It has a method called execute, and we give it a string, and that is the string is in SQL. So that's the inner part. That's the standard part. That's the part that more or less always works for all databases. If we weren't connecting to an SQLite database, but to something else, we'd import another package. We might have to have a few more arguments to the connect methods, like what host does it live on, etc. But then after that, we could execute these kind of things again, more or less in the same way. Right. And this inner part doesn't change. If I go to R, I can have interfaces with R too. I think it's called RSQLite or something like that. That's a package there. The inner part, the SQL is the same. Right? So that's nice. We're learning one new language, but it's portable. Yes, it is. So there's a way around that. So we're going to go through. Yes, it is payable. So there's a way around. So you can do basically giving an array or a list of rows to dump in as one. And it actually goes by execute many rather than execute. That, however, it's not standard SQL, but most interfaces have something like that because it is very painful. So let's look at some of these commands, these inner commands. So just forget about Python for a second and just look at the inner commands. So we can create tables. This looks so much nicer without all of Python, but we need some way to connect to the database. So create table is pretty simple. In this case, we had create table pets. We had 2 columns. One was named name, the other was named type. Both of them contain text, so that's how the syntax go. The general one, so this is SQL. SQL is, at some time in the history of programming languages, they started numbering the generations of programming languages. This is called a fourth generation. What they meant by that is that it looks a little bit like human language. After fourth generation, they stopped numbering the generations, because I'm pretty sure we'd be at 12 by now, and people didn't really care that much. A few things to know, though. It's a little bit verbose. That's not bad in reading it back, and after a while you kind of get used to it. It is actually, I think, more of a benefit than not. It's case insensitive. So what I've chosen, is kind of usually done, is that if something is capitalized, it's a keyword. It's like part of the SQL language. And if it's lowercase, it's an identifier that I chose. So I chose to name this table pets. So pets is lowercase, just so you see that. You could, right. So that's what I'm using the cases for. Create table could be lowercase too. It would still work, but that's just something to show what's part of SQL, what's not. Yeah. Yes. You should not name your table table. Now, it'll usually work because it goes, well, you've already said table, so the next one must be a name. But you're just making it hard for yourself. So there's, and yeah, so don't call your table integers, don't call it text, right? Yeah. Even, luckily there's no pets in it, but it's like, yeah. It's standardized, this SQL stuff, as I said, but there are mild differences between different implementations, so keep that in mind. So we're going to look at a few common commands of this SQL. Create, that's this one. Drop, which gets rid of a table. Alter, which changes the table. Insert, which puts something in it. Update, updates a row. And select is the way we get things out. So here's the create command. And I took this from the SQLite website, and I blew it up way past its resolution. But in any case, you create a table, you give it a table name, and then between parentheses, you do column name and column type, and then comma separated. So we saw that with the pets already. Create table, pets, name, text, type, text. And there's a handy extension of this that works as well. That doesn't complain if you create a table that already exists. So if you're opening a database and you don't know if it was already there or not, create table if not exists, and then the same stuff. That's name, text, type, text. This is really where the verbosity shows itself, right? This could have been a single plus or something. That's not the nature of a fourth generation language. So there we go. Make sense? Okay. Drop is even simpler. Oops, we didn't want that table. Drop table, table name. So drop table pets, everything is gone. You want to be careful with that because everything is gone. Correct. Yes. Yes. So in that one database, that one file, you could have several tables, and they could actually have relations. So this is actually a fairly efficient way to store things. If you have rather than doing, like, say you have. Anyway, you could easily port your database now from one place to another by just copying that one file. That's nice. It also means that in this case, I don't think there's a way to have tables from different databases relate to one another. So that's, you need them in the same database. Yeah. What if we wanted to change a table? Say we have our name and our type of pet. Say you want to know what their age is too. Well, there's an alter command. So alter table. Table name, add column, column name, column type. So it looks like this. Alter table pets, add column age integer. And that just adds a column. I am not sure. It depends on the database type, whether it ends it at the end, which is where I would expect it, or at the front, which some of them do. And the reason that that's not standardized is that there shouldn't be an order. They're named, so it doesn't matter where the column is. They have a name, and that affects where they are. Yeah. You can add one. Now you can insert a row. So we've got our columns. Now we insert a row. So you can set insert into table name, values, and then the values between parentheses and comma separated. So insert into pets values Nala, dog. There's supposed to be an extra quotation here, 4. And so that inserts a row with the values Nala, dog, and 4. Okay, that's what we saw in the initial case too. If you want to change an existing row, you have to use replace. But there has to be a way that it can identify that this was the one you wanted to overwrite. And we'll talk about unique IDs in a little bit later, but that's what you need to be able to replace something. Because who knows that if I want to do this again, maybe you have 2 dogs that are called Nala. It's a possibility. And they might be born in the same year. Updating a row, update. This is a little bit different than just replacing. Replacing is the whole row. I can update parts of a row by using this update command. So you update a table and you set a specific column equal to a specific value. But how do you know which row it is that you want to affect? Well, that's where the where clause comes in. So you have where expr. Expr stands for an expression. So it could look like this. I could update the pets table, setting the type to cat, where it was dog before, where the name is Nala. So it just looks for the rows, all the rows where the name is Nala, and there it's going to change the type column into cat. It's not a very good way it's not very specific, because if there are several animals called Nala, again, we're affecting all of them. So again, we'll see this need for a unique ID for rows, and we'll see how to do that in a little while. Yeah. There, in SQLite, all you can do is add columns. In other databases, there's other alterations you can do. So you could, for instance, change the size. There's only text in SQLite. In other databases, you could say, here's a text that can have at most 200 characters. And then the alter command would be able to say, no, I need 250. Right? It's a different kind of alter. SQLite can't do that. But yeah, so that depends on the, in our case, alter can just add columns and nothing else. Right. Because it's the standard SQL. So in standard SQL, there's other alter commands. They just don't work in SQL. So that's why it's so verbose. And that's, if you were using, say, MySQL or Postgres, you'd be able to do more things. Yeah. Mm-hmm. Not really, no. You can come up with something that's equivalent, but you'd essentially be creating an extra column with numbers in it. Yeah. Okay, so now we've put stuff into the table. Now we want to look up specific rows. We can do this, well, you should use the select command. So you don't have to select the whole row, you can do just specific columns. So then you either give the whole row, that's the star that we saw a few times already, or you do column names, comma separated. What table you want to select them from, so you select columns from a table name, and then you probably don't want all of them. You might want to select them on the basis of an expression. So again, there's a possibility of a where clause. So we could do select name, type, and age from pets where the type is cat. We list all the cats. We could select everything from pets where the type is cat. If we don't do a where clause, we can leave it out. It just selects everything. So if we do select star from pets, we get our whole table back. Okay. So especially when you have large tables, it's good to be selective, I guess. Finally, we're going to look at databases with more than one table. What if I want to combine them? When I want to say, okay, here's a table, it has like 10 records. There's another table, also 10 records. They belong to one another somehow. How do I do that? How do I create sort of a composited table? Do I have to read them in Python, create a new table, and write it out? No, that would be sort of redundant. So there's a join or inner join subcommand, you could call it, in this select, where you don't just have one table name. You could have several table names. You can join them together, and you could say what the basis is of joining them together to make sure that, say, you're always talking about the same entity in both. And that's where where comes in. So for instance, if we had a table simulations attributes and another table called simulation paths, and we wanted to join them together when their simulation IDs match, that would be a join. So another thing that's kind of nice to join, and I almost always do that, is that you can give an alias to tables. The more tables you have, the longer their names are going to be, and you want to be expressive and say quite specifically what the tables represent, because there's no other way to comment in SQL or in databases. So this is a long simulations attributes, a very long table name. So on the spot here, I'm putting in an alias, A, so that when I want to select everything from the table, I just say A.star. That's everything from A. And then from the simulation paths, I only wanted the directory. But I don't want to type simulations path dot directory is very long. I just want to type B. And it's also useful in the where clause, so that it can be A.simulationsID, B.simulationsID. So the idea here was already that we have simulations running, and they have attributes like their parameters. And then there's another table that's stored where, in what directory these simulations actually ran. So that's the simulations path. And I want to know, basically that's a separate table that's not touching the original table, that just has the parameters. This puts them together into one virtual table and gives the results. You can go to SQLite.org for more reference on these commands, but that's does that make sense? So that's the SQLite, the inner part, creating tables, columns, rows, inserting and selecting them back, and combining tables with relations if you want to. Okay, so now let's look at how we interface this with Python. So in Python, we have the SQLite 3 module, so we import that. And then we can open the database with connect. So this opens it. It might not exist yet, and then it's just an empty database. It might exist already, and then we can read from it or write from it. So it opens it, read-write if you want. We have to store the results somewhere, so we store it in a connection object, which I've called con here. And then con is just a sort of an abstract idea of I'm connecting to a database. I'm not actually looking at anything in the database yet. So there's this concept of a cursor in databases, where those are the things that actually look into your data. So you're supposed to go and make a connection, then create a cursor, and with the cursor you can look at your data. That's an extra step that is usually not needed for SQLite. It's more useful in other contexts. So what I've chosen to do is to not follow the standard that says you have to create a cursor from your connection, but to use that, you can use the connection as if it is a cursor. In other words, you can use the connection to start looking at your data. It's a non-standard extension of databases, which makes the code a little bit easier to understand when you're just starting. And so it's a little clearer, I find. Okay. So suppose we work with the connection, then that connection we can use to execute commands. So we do connection execute create table, and connection execute select from table. In each case, they return again something that's called a cursor. In the first case, creating a table, we don't really need anything back. It either succeeds or it doesn't, and if it doesn't, it'll throw an exception in Python and we'll see it fail. So if I'm trying to do it and the table already existed and I did not say if not exists, it'll just exit, done, right? Or I can catch the exception in Python if you know how to do that. But in the case of selecting things, I do need to get that stuff back. I need to get those rows right into Python somehow. And so I have to assign them to this, but both of them are like execute can only really return one thing. Well, it's Python, not really, but it only returns one thing. It returns a cursor. So where I would want in the second case for the select to probably just return me a list of these rows, it can't, because in other cases it just has to return nothing. And so that's that. So the abstraction here is that it returns a cursor, and then in the second case I can query that cursor to give me the actual results. It's kind of weird, but that's how it works. So once you've executed select, you can use this cursor, called cur here, to get your results out. So if you just want the first line, the first row that it returned, you do fetch 1. And if you're expecting only one result, they'll give it to you. But if I want all of them, I have to say cursor.fetchAll. That sounds like you would always want to do that, but if this is indeed 10 million rows, maybe you don't want to do it. So then, of course, there's an intermediate one, fetch many, and it gets a partial list. You can say how many you want at a time, and then keep calling fetch many until you've gone through your batch. So just to give you a little example. So here I'm connecting to the database again. I'm assuming I ran my previous scripts where I created the pets table. And I'm selecting name type from pets where name is Missy, and I execute that. So both in SQL and in Python, you can use double quotes and single quotes, as you might know. But of course, if you mix them, that gets messy. So you want to make sure that if your SQL is in double quotes, then your strings are in single quotes in SQL, or vice versa. So I've executed it. It gives a cursor. I've just called it C here. And I'm just fetching one element from that cursor and printing it. So it should output something like Missy and cat. So that's those are those two elements of the row. Make sense? I'm just getting one. I'm not getting in a whole array, and it returns it as a tuple. That means that I can't change anything in it, which is, I guess, a good thing, because this is the actual data. So when we're filling the database, as you already noted, we had to keep execute, insert into pets values, and then just type them. It gets very, very cumbersome. Plus, this has to be a string, so I have to make sure that I concatenate a string. It's just horrible. So there's a command called execute many. So you take your database connection, execute many, and then insert into pets values. You give your SQL with placeholders. Those question marks are placeholders. And then you have to give a list of tuples, and the tuples have to be the size of the number of placeholders I have. So 3 placeholders, each of these tuples has 3 elements. And so not only does it is sort of shorter than this, it also makes it easier to just have integer elements in there. This is kind of silly, because the 4 here is the character 4, which I somehow had to convert. Because the table has integers to store, it will then convert that text 4 back into integer 4. It's kind of silly. This does this in one case. Okay, makes sense? So if you're filling things, if it's a loop and you're filling them one by one, you don't really care. But if you quickly want to make a table, this is the way. Okay. As I already said, you could actually have multiple processes opening the database, but it's keeping a consistent look, a consistent database at any given time, so you never get a partial row or something like that. How would it know? How does it, like, if it has to stop everybody each time for doing any executions? Say I'm doing this set of 4 inserts. If every other process has to wait until each execute is done, that takes time. That creates more bottleneck than needed, and that's kind of where this idea of a commit comes in. I don't really mean it until I say commit. So these 4 executes have not been done at all. They're just sort of stored in a to-do list. And when I say commit, that's where the database locks the database. Nobody else has access except that one process is doing the commit. The commit can do its executions, and then it releases it. Right? So that means that the bottleneck is only at the commits, which is 1, instead of at 4 spots. And that's better. So this idea of commit is very important. If I don't commit, I basically can't trust that the data is in there. It might be in there, it might not be in there. You can't trust it. So once you're done writing to a database, you'd want to close it like you would close a file. And so, again, it's very important first to commit. If you close before you commit, you might lose your last interactions or transactions with the database. Commit's important, and then close. Okay. Make sense? Okay, so that's the how. That's sort of how to do the nuts and bolts. There is a whole field called database design. And I guess it reflects the fact that things aren't tables. Like, not all data is tables. But most data has relations. And so how to map sort of real data out there to a database made out of tables has a lot of history and a lot of best practices associated with it. And so if you know what you're going to use your database for, it's best to design it up front to avoid a bunch of pitfalls. So basically the question is, how do we set up our tables? And by thinking about that ahead of time, it avoids a lot of trouble. Trouble in terms of, oh, I have a column in this table that I don't even need, but I put it in there. Well, in SQLite, it's there forever. There's actually no remove column, so now what do I have to do? Bad choices of naming can bite you, because maybe I have 2 columns that have almost the same name except for 1 character. That was not a smart idea. Somebody did it. So the more you can think about these kind of issues ahead of time, better. But you can't just start thinking. You need some guidelines. So there's some best practices that are good to know, and that kind of make sense to deal with this design decisions. What's going on here? So first, a few things in terms of terminology. There's this thing called null. Basically, any field can be null. Null is not 0. Null is I don't know this value. It's either not be entered yet, or it was never there. It's a missing value. So it's an important concept, because a missing value is not the same as 0. It's not the same as a default value. It's just I didn't know that, and so it's its own thing. Languages like R, which do statistics very well, deal with unknown values, missing values natively. Languages that thought they were more numeric, like Python, don't have a native null in the same way. They have a none, which is kind of similar. It's missing data. Another thing to know about terminology is this idea of a schema. People talk about schemas. Basically, it's the definitions of the columns of the tables. So if your tables, what columns do I have? What type are they? And which columns are the same in different tables, which relate to one another? That's the schema. It's really not more difficult. So if you think of your empty tables, what would they look like? That's your schema. Rows, records, relations, tuples. They are all the same, but people will use different words. If you think of a table, a row makes sense. This is a row. If you think of customers on a website, records make sense, because every customer has a record. Relations also make sense. Every row is a relation between the values of the columns. Tuple also makes sense, because in Python we get them as tuples, and tuples are just single blocks of different elements. So they're all essentially the same. And I might sometimes use the words interchangeably. Likewise, columns are sometimes called fields and are sometimes called attributes. The idea of an attribute makes more sense if your rows are entities, like people, and people might have a name, they might have an age, they might have an account number. So those names, account numbers, those are attributes to the people. Fields, I don't know why that's more appropriate, but again, people call them fields. And columns always make sense. They're columns. They're essentially all the same thing. Key. A key is we'll see keys in a second. Keys are a special kind of column. Usually they are things that uniquely define the row. So they're like a unique number or something like that. But something that identifies them as an identity. And they're very important because you could have a column of attributes for a person here, one type of attributes, and other attributes in another table. And somehow you'd have to know which person is the same. That will be the key. The key is going to go, this is person Ramses, this is also person Ramses, but the same Ramses, not some other Ramses that are there. Okay, so we'll need special keys to distinguish entities. It sounds similar like the next thing, which is an index, which you might think is also a unique way to identify things. But in databases, an index is really a way to improve lookup. Essentially, it creates a table to quickly find a key rather than anything, and that's called an index. And so it's a lookup helper. And so it's not that essential in understanding databases. It can be essential in using them efficiently, but we won't really see any use of it. So the key is key. It's a unique identifier or something that can identify a row in a table. Okay, so database design. Here's a table that would work for our simulation data, for our argon. There's the number of particles, there's the temperature, there's the density, it's called rho here, the initial random seed, the time it's run, the time step, the pressure that came out, the energy that came out, and a column for the system. It can do more than argon, so I have a few nitrogen simulations in here as well. This is one big table. It would work, but it does not follow best practices of database design for a number of reasons. If all we wanted was the end result, and that was all that it was a publication, this would work. We would put this in our publication and say, this is what we found, right? It's clear. But we'll see that there's a few things that aren't clear from this if this is a dynamic database. But before we do that, let's look at our simpler example. So let's look at pets. So we have 4 pets. We put in their ages because we altered the column, altered the table to have a column. So Missy is 4, etc. There's actually quite a bit of things that aren't ideal if we were actually keeping a database of pets. Say we were a pet store, this would not do, and it would not do for a couple of reasons. First, there's cats in there and dogs, but each time I add a cat, I have to type cat. What if one is a real cat and the other is a lion? We're not talking about pet store anymore, I guess. But I just put in cat quickly anyway, because that's like I didn't want to type an extra character and have lion or something like that. And what if we wanted to change cat? Maybe we figured out, okay, we're now going to have lions. We better now not call cats just cats. That's too ambiguous. We would call them domestic cats. Then we have to go through the whole table and change cats to domestic cats. What if I need to have a bilingual way of doing this, and I have to put chat and chien in that? How do I do that? Well, it's not there. So having this duplication is bad, and is also in terms of maintenance can be an issue. So what you should try to do, that's design principle 1 for databases, is for every record to be unique. That's the first thing we want. So if I added another kitty cat, I have an issue. I can do it. I can put it there. Here's a table with 2 kitty cats. They happen to be both 3. But the question is, are there 2 cats called Kitty with the same age, or did I accidentally just enter it twice? And from the table, I can't see which is which. Right? When I put it in, I probably knew. But if I am allowed to just put in duplicates, then the database won't warn you saying, oh, you already have Kitty in there. Okay? So we want every record to be unique for that reason. If they were unique, there's only one. But what if there are two kitties that have that are cats that have age 3? Then how would I enter them and still have a unique row? Well, that's design principle 2. It follows from the first one. If it has to be unique, but all the fields, all the columns have to be the same sometimes, we just give them an extra unique key. So instead of doing this table here, I left out the 5th kitty. Oh, wrong way. I add a column that is just, in this case, just a number. It could be something else, but usually people use numbers because it's the simplest thing. It's an ID. It's called a primary key. And it identifies exactly the cat. So now I have a possibility to put a second kitty cat that is 3, and we'll get ID 5. Or it can go, oh, I have to have ID number 2, cat number 2, and it is called kitty cat 3. And in that case, I can tell the difference between these. Okay. So these are just called keys. It's just an integer in most cases, and we'll only use integers here. You could do other things, but it kind of gets silly. Now, you don't really want to, this has to sort of be automated, and it should be automated. When I enter a new pet, I should not have to look at a table. Oh, how many pets were there? 4. So the next one, when I insert, my ID is going to be 5. And not only is that silly, I'll make mistakes sometimes, or even worse, I might be entering a 5th pet. Another application might also be entering a 5th pet, and now we're just both entering fields with 5, and it's wrong. So we want this to be automated, and that's this idea of an integer primary key. So if you define it not as an integer, so you would normally create a pets table with an ID with ID integer, but you give it this extra clause called primary key, then when you insert your values and you insert instead of a number a null, remember this special I don't know what it is null, then it will fill in an integer, exactly the next integer that it should be. And because it will actually not do it at this point, it will do it at the commit, so that you never have this issue of different applications updating the same database and giving the same ID. Right? So ID integer primary key automatically generates a unique ID. You could, after your insert, you could ask, oh, what was the ID? There's ways to get that if you need it right away. But that just solves the problem of having unique records and not having to number your keys by hand. That's right. That's right. If you had, there's ways to give default values to these things as well, and null would invoke those default values as well. So you could have you mostly have cats. You could have a default value of cat for the type, for instance. But it's mainly very useful for the keys, the primary keys. Okay. Another thing that is very useful, because especially to sort of argue and think about these tables after the fact, is to have their records be what are called entities. Now, entities kind of vague as well, but they're a thing. So in the case of pets, that was clear. A pet is a thing. Right? Each row, each record is one thing, which also makes it natural that they should be unique. Right? It's either a thing or it's not a thing. It's not a half thing or a double thing. But if we looked at our simulation data table, they weren't really one thing. Let me just put it back just to see what could go wrong. So look at this row. So I've got some parameters here. Well, these are parameters. Actually, t was not a parameter. It's something that comes out of the simulation. So my number, my row, seed, time, I already knew those ahead of time. But then after the fact, I have to go in and put in the t and the p and the e. So it mixes what are parameters and what are outcomes. And so those are different entities if you think about it. You could think of making two tables. One is parameters, the other is the outcomes. And what I like to think of it like, when is something separate enough to be an entity? When am I going to put that data in? My parameters I can put in on day one. Nothing has to have happened, but then afterwards, only when simulations have run, I put in things. The same with like your bank has a record of you, but in that record doesn't show your balance. That makes no sense. That would be in a separate table because it gets updated in a different way or in a different case. It's not always easy to see what the entities are that you should have, but you should strive and make them be things. Okay? It doesn't always work, but especially if you have a table that is a true relation. So I have a table of people, and I have a table of eye colors, and say I have a third table to map people to eye colors. Well, that's a 2x2 matrix of some sort, right? But none of them, they're part of each of them being a relation. None of them are things. They are just basically arrows between one another. So if something is a many-to-many relationship that a table embodies, then you can't really have them be entities. But that's pretty much the only exception. Like if anything else, you'd want them to be entities. Okay. Fourth principle, don't repeat yourself. So don't duplicate data. So in our table here, everything is unique. That's great. But cat happens twice and dog happens twice. And I already kind of hinted at that being wrong. And it's wrong for maintenance. Say cat should become domestic cat. Mistakes are also easy to make. What if I misspelled dog and there's a what's next to the D, an S, so it's a SOG. Nothing would detect that mistake. So the way to fix that, to get rid of the duplication, is to use foreign keys. And let me show how it works first before I say exactly what a foreign key would be. So I replace my types with numbers again, with integers. Really, they're keys. The fact that they're integers is just because it's easy. So my cats become type 1 and my dogs become type 2. And I need a second table to explain that type 1 is a cat and type 2 is a dog. This looks worse, and it is for this example. It's like kind of silly because I have more data here. I may not be duplicating things, but it's more stuff. So apart from these buts, it does mean that if all the cats now have to be replaced by domestic cats, I just have to change this one item. These all know that they're type 1, and type 1 is a cat. If I wanted to have English names and French names, this table would just have an extra column, and I just add the French words for them. I don't have to change the actual pets. Nothing has changed to the pets. It's the same concept of when do I change things, right? Will I change names sometimes? Well, maybe the names are a table. Right? That's it. So there's one important thing though here. If these are just integers, then I can put anything in here. So what if I enter a 3 here? It doesn't point to anything in pets 2. And now I have, again, a maintenance headache. Like how am I going to do, how am I going to get properly maintained databases if I can have IDs that don't pertain to anything? So that's this idea of a foreign key. You can tell this table, your type IDs are a key that has to occur in this table over here. Okay. So that when I insert something and I give it a 3, it's going to go, oh, that should occur in pets 2. Pets 2 doesn't have it, error, exception thrown, and deal with it. That's why it's called a foreign key. So there's a key here. Type ID will be a key, an integer primary key. These also will be keys, but they're foreign keys. They're keys that point to this table. Yeah.
Say, for example, it's possible to get the same name, right?
No, so I would say that actually doesn't make sense, right? It doesn't really make sense to have, like, I meant names of types, but not names of, if it's it's your given name to an animal, it belongs to the entity, right? There's no point in, I'm not repeating Missy. If I had a 5th Missy, it's not really a repeat. It's just a coincidence that there are 2 Missies. So you don't want to codify coincidence in a separate table. They are both just by accident called Missy. They're just, that's fine. Does that make sense? So so duplication doesn't mean duplication of the exact data. It means duplication of things that are the same thing. These are both cats. That's the same thing. It's not an accident that they're cats. I looked at them. They're both cats. They belong to the classification of cats. But the fact that they're called Missy has nothing to do with the fact that the other cat was called Missy. So accidents or coincidental duplication is fine. We're not trying to minimize our number of bytes here. That wasn't the point. The point is to avoid mistakes by having to enter the same data twice. Okay, so how do you actually do this foreign key stuff? So there's this depends a little bit on the database. So this is SQLite specific. The first thing we have to do, unfortunately, SQLite actually doesn't enforce the foreign keys. It just goes, you want to put in a 3 there, and there's no 3. I don't care. You do what you want. So if we want to enforce this, we have to execute a pragma to put the foreign keys on. It means that it will now, when I create a new row, it will check that my foreign keys occur as a primary key in another table. And then in the definition of the table, I have to add this link between the two tables. So I have to say foreign key type ID, so that's my foreign key, references the type ID in another table. And just to be even more specific about that, this is how it would look. So I'm executing my pragma, foreign keys is on. I'm creating table pets2 with an integer primary key type ID and a name, which is a text. And then I create my original table pets. I'm using the triple quotes here. If you're not familiar with that, that allows you to have multi-line strings in Python. And especially when your tables get a bit long, it's a nice way to just format your columns as rows. So here's my pets. I have an ID, integer primary key. I had that before. A name, a type ID, integer. This is going to be a foreign key, but in the definition we don't see it yet. It follows later. Age is an integer. It follows right here, where I say foreign key. Oh, by the way, so this is by the way, my type ID here is a foreign key that references pets2's type ID. So I don't have to say in this table that it's going to get referenced somewhere. But I do have to say in the creation of the pets table that this is a foreign ID that belongs to this table. So there's a design here. You can't, after the fact, goes, oh, this column should have been a foreign key for something. You kind of have to build that in. That relation is sort of fixed with the tables. And then I can insert the values, and I can insert these values. So here are the values 1 and cat. Those are the types. Here are the pets. In this case, I've done everything correctly. 1, 2, 2, and 1 are actual types. If I put a 3 here, it would raise an exception and say that's not allowed. Okay. So I've created my foreign keys. They're pointing at one another. But now I have to, yeah, sorry. No. I could do that, but it makes it a little trickier. This is what you should do. This is not entirely what you should. So if you put a null here, the 1 and 2 will be automatically generated. But the next step then for me should be to check what the ID is of a cat. Because when I'm inserting this, I only know that Missy is a cat. It could. Like we don't know if there were other things already in here in the table, right? Now, if you're thinking of say a database that's behind a website, what it would do is would say, okay, just null it. They're cats, they're ones, and then there'd be a drop-down menu for your cats and your dogs, and it would be a 1 or a 2 automatic. Well, not automatically, but it would do that for you. And then you can only select correct ones. But because we're allowed to put in integers, we would have to check after this. We'd do a select pets where name is cat, and we'd find the type ID, and we'd use that type ID to insert it here. Does that make sense? Well, that way I'm sure. Oh, this also enforces that they have to be different. Yeah. So it helps in that. And if you ever do just use null, it still works. So yeah. It has both the uniqueness and the automatic increase. Okay. Now suppose that we have those two tables, but we want our original table back, maybe just for displaying. that's where we do one of those joins. So we're going to do pets, and we're joining it with pets2. But these are two tables with different sizes, right? Where were they? Here they are. So we can't just sort of paste them together. It would make no sense. What we need to do is to say, okay, if you have a type ID 1, you get an extra column called pets2 name, that is cat. And if you have type ID 1, again cat. If you have type ID 2, it should be dog. So we have to basically select the right foreign key to match the actual key. And so that's the on clause that is in here. On. So I'm taking those two tables and pasting them together, making new rows with more columns, such that pets ID is the same as type 2 ID. If I didn't do an on, what it would do here is it would create 8 rows. Every possible combination of a row on the one and a row of the other. Which is, maybe sometimes you want that, but typically you don't. You want from those 8 possibilities only the ones where they match. So if you think of it that way, you formulate it like make a big table with every possible thing and then filter them such that the type IDs match up. It's not what it's actually doing. That would be a very inefficient way for the database to do it, to create this massive table and then prune it. But it is the semantics of it. You're joining it, and then you're filtering it. Because it's one statement, the database will say, I know exactly what you mean. I'm going to only create the ones that match. That will be done properly. And then I fetch all of them, and I can see the table. Does that make sense? So this is we have a few more best practices. But this is the basis of having multiple tables in the same database. The tables are responsible for different kind of entities. One is a type of animal. The other is the animals. They are related by these foreign keys. I can get them back. I can custom. That is the mechanics of most of this stuff. Makes sense? Okay. Let's take a little break. It's 2:35, so let's continue at 2:50. If you want some water and you brought something, you can go out that door. There's a faucet. If you want to very quickly go get coffee, I hope it's not somebody else's break, you could go downstairs, but we'll start at 50 again with the rest of the material. Okay. All right, you can continue, I think. Where we were doing tables, foreign keys, joining them. Right, and we were doing some design principles. So here's another one for you. Use clear table and field names. That sounds like, why wouldn't you do that? But it's worse here than in other programming languages because you can't really put comments in a database. I guess you could make a table that's called comments and then put text in there, but that's about as good as it gets. So your identifiers of your columns or your fields better be sort of clear and unambiguous. You don't want them to be too long because that means that it's easy to misspell them. But use unambiguous stuff. Plain English, for all of its faults, English is a very common language, and so you have a good chance that even your coworkers will be understanding what it means. Don't put spaces or special characters or reserved SQL words in there. It's possible to have column names with spaces in it and with quotation marks and stuff. And then there's ways to have those be accepted into the SQL, but you're just putting unnecessary difficulties or extra tasks on your shoulders that you don't need. So avoid those and stick to some sort of convention. It doesn't really matter what it is, but here's some examples. Pets2 does not explain what this table is, except that it's also about pets. What it are the types of pets. So what it should have been called is something like pet types. Age is also somewhat ambiguous, like is it the age in seconds, in years. So sometimes, in this case, I don't really think it's that ambiguous, but if it is, just make the name something like age in years, so you know what you're talking about. Try to avoid acronyms and abbreviations, even if they're very, very common, or if you just invent them because you did not want to type C++ 03 or 11 compliance, is not a good enough reason to make it CPP 0311 because people will not know what it means, and you will not know what it means after the fact. So, what I mean by stick to a convention is that I chose to put underscores in here. You might have other conventions. You might want to put them all together. It's nice if your database, all the columns and all the databases follow the same convention. So I don't have to think about, oh, are the words separated by an underscore or not, or does capitalization matter or not? Just stick to some. So clear tables and field names, just so it's kind of self-evident what the tables mean. They'll never be perfect, but it doesn't have to be horrible. A sixth design principle, which is kind of doesn't fit well with the scientific computing idea, is that column values should be what's called atomic. So atomic really means that you should change them as a whole. And so I'll give you some examples. The age changes as a whole. Next year, this will have to be 5. By the way, this shows a poor design of the table. The table should have their birth year, not their age, anyway, but still, the age changes as a whole, as one. So I don't have to change part of it. The type here, cat name, this might change. It only will change completely unless there's a spelling mistake. Cat will become domestic cat as a whole, not no. Add a D, add a 0, add an M. In case that wasn't clear, that also means that if you're storing things like arrays, that is not true. If you have grid data, then you're not going to, well, depending on the application, you want to be able to manipulate each point in the data. And this is why, I'm on the right spot. This is why it doesn't really make sense to put arrays in databases or sets of things. Like you have a set of things. Say I want to know which of those animals have to be fed at midnight. I guess there are some nocturnal animals in there. I could put an array. I could just write them in an array and say that's a column, right? But I get another animal. I have to add to that array inside of the column. So that's not atomic. That's not changing the whole array. It's trying to change the substructure of a column. So a column value really, ideally, should not have extra substructure. It can have different elements. For instance, what might work is, although you don't see it much, is a location, like longitude, latitude. That would change as a whole. It's one thing. You don't just change the longitude unless you go exactly north, right? So arrays don't really fit, and that seems like, okay, now you've lost me. I'm not using this for scientific computing or for anything grid-based or images or something, which is true. But it doesn't point to a thing that's wrong about databases. It tells you more clearly where the division lies on what you should and should not be putting in a database. You should not put image data in a database. You should put the information about the image in the database and a pointer to where the image is. But the image itself doesn't have to be in there. The ways to deal with sets is actually different than just putting them in an element. You make another table that creates it on the fly, more or less. So this one, in pure database design, if we took this to be applicable to scientific data, what we would have to do with this grid data, so say there's temperature in an X and Y grid, is every point in that grid is an entity. So I'd have a table of grid points. The grid points would get a primary ID, just numbered sequentially. Then there would be an X coordinate column, a Y coordinate column, and a value of the temperature. That is redundant, obviously, especially if it's a regular grid. Wasteful, but that would be the proper way to do a database of that grid data. It's inefficient. It's unnecessary. We just want that grid. So But that would be the pure database way to do it, because I could just now change the temperature at one grid point. I just find the right grid point with the right x and y value, and I change that one atomic value. Does that make sense? Don't do that. But that would be if all you had to store things in were databases, that's how you would do it. That's the official guidelines of how to do it in databases. We have better tools to store binary grid-based data. SCDF, HCF5, that kind of stuff. Your field might have better ways to store your genomic data. Your genome should probably not be in there, because there's things that change. So they are probably not the best spot for a database. So we're using this rule not for how to construct your grids inside a database, but what to leave out. Just do it differently. All right. There are more, but I forgot them. So common sense is another one, but that's and you know, I actually started using databases mostly when I was suddenly faced with the task of creating an education website, and I didn't want to create it from start, so I took somebody's open source solution, and it was all tables. And it took me a while to get the hang of it. But knowing these design principles or reading up on them, so now I understand why there are 50 tables, because they're all different entities. There's a course, there's an event, there's a student, there's an instructor, there's a mark, they're all different tables, and they have relations. There's very little grid data needed there, luckily. Yeah, it's by doing and looking at some of these designs yourself that this becomes a little bit more natural. But it's good to know these things ahead of time when you're working with it. Okay, so let's try and see what we can do. This is a good spot to make that bridge. In a case where we have data that doesn't necessarily fit very well in a database. So this is our old use case of the parameter sweep of the molecular dynamics simulations, so the simulations of argon. So here are my green balls again. I should have made a movie where they're actually moving that but didn't have time. So what are we supposed to do here? We're going to perform simulations of argon, and each of them will give a measured value of the pressure. So we set the density, we set the temperature, we get out the pressure. What we want is the pressure as a function of the density and the temperature. So we also want to save a record of the intermediate measurements, so the energies, etc. And in the original case, we also wanted to keep a record of the trajectories, which I said I had thrown out. So we'll vary container size, so that will change the density, number of particles, possibly, and temperature. And that potentially gives you a lot of data. Remember, we're getting time trajectories, or these timestamps. So for every time that we're simulating, we know at least those 5 values, I think, that were spit out. And then once we have all that data, we want to be able to select specific points. So we have a temperature grid. Maybe we want to look at a specific temperature and just plot those pressures as a function of density. Or maybe we want to look at a range of particles. So maybe we want to see when the pressure becomes negative, which I think means that the thing is freezing. So before we can design our database, or know even what we want to store in the database, we should think a bit about how we're going to do this. So we imagine these are too many simulations to just write one big script for, and it's done. We have to run them on supercomputer. We have to do batch jobs and do all the things that we like to do on Niagara. So you go to the whiteboard and you start sketching what you have to do. Probably you try it first once, but you go, okay. So you start with this. Okay, I have a set of parameters, and then I've got my runs, and I'll get outputs, and I'll get trajectories. Again, I threw them out of the code, but you get trajectories, and you get your measurements, so your pressure and your energy and stuff. Okay, that's what we want. But that's conceptually what we want. But Where do we get the parameters from? Well, when we're done, we'll do plots and select some parts, archiving, write your paper. So once I know my set of parameters, I have to create these batch jobs because everything is a job, right? And I have to give it to the scheduler. So there'll be some sort of script here that will take my set of parameters and create the actual runs. And then once my output is done, I probably need another script to create my plots. And then when that's true on a higher level, but each of these lines represents a single simulation. So there's actually more than these, 10 lines or so. They actually have a whole bunch of stuff themselves. So this is a simulation run, but it will take an input file, it will produce a trajectory and some other output. There might be error that it produces. We need a batch file that tells us how to run. So even that has a certain complexity to it. And then if I think about this batch file, that's some batch file that I didn't specify, but it has to be a Slurm batch file that we can give to the scheduler. My input file will contain number, density, temperature, etc. The output will look like this. The trajectory will look like something else. The error. So there's a lot of stuff floating around once we've done all of these simulations, or as we're doing these, right? And so the question is really, what of all of this stuff do we need to keep in the database? Right? Can it help us keep track of this? And if so, what are we and are we not going to put into here? So you don't have to have a database for this, obviously. You could just have a whole bunch of scripts and carefully keep some text files or some Excel sheets where you keep track of everything that's done, and you have your email notification set up so that when a batch job finishes, it sends you an email, and you go to your Excel sheet and say this one's finished, and that's the data. Sure. And you might be at a scale where that works, but suppose that doesn't work. Let's just suppose that we really like the idea of putting a lot of the automation into some Python scripts and some databases, and then maybe some things are still left on the file system. So we'd have to design a database for it. What do we store in the database? What do we not store? And so the central quantity question is going to be, what are the entities? What are the things, right? Because we will have tables, they have to be things. And what are the attributes of these things? What do we have to store? And how are they linked? So that's where our foreign keys will come in. But we've already sketched this. So to be honest, every box is a thing. That was kind of nice. So the parameters are a thing. The trajectories are a thing. The measurements are a thing. The runs can be a thing. Basically, anything graphical here can be a thing. The question is more, what do we want to keep or what belongs there? So parameter definitions are in there. Maybe we have our grid. Our grid will be refined at some point, maybe. So we want to specify a range of parameters of densities and temperatures, and then later specify the fineness of the grid. And then there's jobs. We want to know what input parameters do we have, what jobs have run, which have not run, where did they write their output, what did they measure. Maybe we want to take that last line with the final pressure. That's not much data. Maybe we can put that in the database as well, but probably not the whole trajectory. Those are some entities that we could put together. Right? So the first thing then that we need in the workflow is our parameters. We have to understand what they are, and then from that we will generate sets that we want to do runs for. So we could design a table that stores parameter definitions. And this is a tricky one. I find this always tricky. You could completely skip this step potentially. It automates some things, as you'll see, but this is your physical system. You know this stuff, right? Or you could just jot it down. Okay, I'm going to take. I have runtimes. I have time steps. I have pressure. I have temperature. Those are just things I know about. I don't have to codify those in the table. And you might be right if you think about that. But the idea here is that we could actually have the allowed ranges of these values somehow in the database. So something like this. So SQLite imported, connects. I'm creating a database called ljproject.sqlite3. It creates parameters. So each parameter has an ID. Again, this is a little bit silly because temperature, density, number, they're not quite on the same. They're very different things, but they all enter into my parameters. So they have a parameter ID. They'll have a name. They'll have units. That's nice. At least I can specify. It's kind of like a comment. And then I'll codify a lower limit and an upper limit to give me the range of the set. So the temperature will range from 80 Kelvin to 340 Kelvin. The density will range from 100 mole per liter to 10 moles per liter. The number density, I want to keep it fixed, but just to be consistent, I just have the lower and the upper limit the same. Runtime similarly, time steps and seeds. So the idea is this defines a grid. In this case, I'm only doing 2 dimensions really, but I could at some point say, oh, let me see how it depends on the number of particles. Maybe there's some finite size effects, so I just increase the number here, and then my scripts will pick that up. I don't know if you'd ever really want that level of generality, but this would be a way you could do that. Seeds, again, you definitely want to do some different random seeds to make sure that you're not seeing artifacts of your random number gen. Commit and close. So this creates just one table with parameter ranges. That's going to be our definition of what we want to study, in a sense, right? That's the entity. So if we've done that, this might be a good point to do that here. So let me run that. So I have my git cloned. Where am I? Oh, one source up. I cloned my DBB19 from before. I did source setup, which means I have certain modules loaded, like GCC and a Python. That's good. And then I could call this script. So that's the script A, just to show you. See, so it's pretty much exactly what I just had. I can run it. Let's make sure I don't have one yet. So Python. There. Doesn't say anything, but it will have created this ljproject.sqlite3, and I'm doing it on purpose here to show you or show off the SQLite3 prompt. So there's a program called SQLite3. You give it the database, and it'll give you some, and it'll allow you to put in SQLite, so SQL statements on a prompt. So you could do this. You could do select star from parameters. We just created parameters. Select, wait, SQLite3, select star from parameters. Hey, what happens? You cannot run it. Oh, I didn't give the name. You have to say what database. There we go. Select star from parameters. So there's the table. Now it's not very nicely arranged. So on the slides I have some ways to make that better, which I always forget. So there's mode column and header on. So if it's something is not standard SQL, it starts with this dot. Those are SQLite3 prompt specific things. I can do the same thing again. Select everything from parameters, and then I look a bit more. So they're in there, and so it's a nice way to check that things worked as they were intended. It's also a pretty nice way to check your SQL syntax. I find, because especially because you're giving just a string to the execute command in Python, and if it goes wrong, yes, it throws an exception, but you're not quite sure if your Python was wrong or your SQL was wrong or where it's wrong. So and then you change the string and run the script again, and it's wrong again. This prompt is a nice way to sort of interactively try and figure out if you got your syntax right. And especially your first few joins and stuff are good to just get your hands dirty inside this interactive prompt. So this is what we got. There we go. That's our first table. That's going to be our definition of our parameter space from which everything else should follow. How do you get out? That's always a good question for program.exit. That's how we get out. Alternatively, there's a graphical interface. Depending on how far away you are from the data center, that works nicely or very slowly, called SQLite Browser. And it'll look more like this. Has a little bit. So nice thing here is that you don't have to know the table names to select them. You just it figures them out. That actually should work too. SQLite browser. Let's see how. Where is it? Here. That's not bad. And then you can go to data. That is pretty bad. I don't know if this is doing. This might be too slow. I think this might be too slow. But if it's not too slow, it kind of looks like that. That's nice too. Okay, so that's our step 1 or step A, defining your parameters, putting those in the table. Fine. Now, from those ranges, I want to create the actual parameter sets I want to study. This is a parameter sweep. Which parameters am I going to do? Now, SQL isn't particularly good at creating ranges. So here we're going to get some help from Python. So we want to take these parameter ranges, read them into Python, create parameter sets, so specific parameters, and put those in a separate table called parameter sets. Right? So we're going to write that, and that's B1. And we could do that. We could write a script that generates, say, 20 values in each of the directions, and write those to a table parameter sets, and that's fine. We're going to hold off on doing that, but that's conceptually what you'll do. You take your ranges, and then you have essentially what will be the seed of creating the separate jobs that you want to run. So you have parameter sets. From the set, you create a job script. You run the job script. You wait until it's finished. When it's finished, you read its output. You put it into a results table, something like that. So it would look like this. I'm connecting to my database. I'm selecting the lower and upper limit for the temperature. So I'm selecting lower limit, upper limit. Those were the names of the columns from the parameters table, where the name is temperature. So the name of the parameter was temperature. And then from that, so that's a cursor that I have not fetched anything from. I'm going to fetch one element. I know I'm going to just get one because there's only one name. The name's temperature. And I'm creating between the lower and upper limit, I'm creating 10 possibilities. So I'm using the numpy linspace command there because it does equally spaced values really nicely. Then I do the same with the density. So I get the upper and lower limit. I get just the first line, but there is only one line, so that's fine. And create 10 elements there. And I realized on the previous slide I said 20. Apparently I took 10. And then I'm doing the same for the number of particles n, t, dt, and s. But I'm just using that I know, and that's not particularly robust, but I'm using that I know in this case that I only have to consider the lower limits because they're the same. If I wrote a more general script, I would do the same thing here. I would notice that the upper and the lower limit are the same, and I would just do one number. But that took a little bit far for a single slide. So I've got a range of values for the t-vals, the temperature values, and the density vals, and then fixed values for these. And then I create a new table called parameter sets. It should probably say create table if not exists, but it does not. And then it has columns where there's a primary key, and I've called that sec with a capital S. That's the sequence. I've done that for a reason that will become clear later. This could have just been called ID, but in this case it's called sec, but it's the key. Temperature that I'm choosing, density, number of particles, runtime, time step, and the seed. And then I'm putting together tuples of T, D, N, T, D, T, and S for every possible combination of the temperature and the densities in those values. So this is a bit of Python magic where I'm creating a list of tuples that I want to store in this file, and then I execute many on that tuple to put them in the parameter set. Okay. So I'm using a lot of sort of Python nice tricks because I have them anyway, and this is not computationally heavy by any means, but if I had to do this without having range generations or list comprehensions or the insert many or execute many, it'd be a lot more cumbersome, but you could still do it. Okay, so this would create my parameter sets. That's great. And if I put them in the SQL browser, it would kind of look like this. Lots of temperatures are the same, but then the densities goes up, and further down, I can't scroll here because it's a screenshot. I'd see the temperature change and the density go through the same set of numbers, and all of the other ones are the same. And I have a parameter set. So now I could take this table and say, okay, let me go over all the parameter sets, read out the values, put them in an input file, and then write a script that reads that input file as a job and executes the LJ application. So that would be step 2, or I call it B2, where you go not just you have your sets, but now you create your jobs. You need Python's help again to do this. We're creating scripts. SQL doesn't create scripts for you, and definitely doesn't submit them. So you could do that. That's good. And it would then generate the input files and job scripts, and then if it's a really nice script, it would S-batch them off to the scheduler. Fine. I'm going to show you a slightly alternative way to do both step B1, so the generation of those parameter sets, and the generation of the jobs in one fell swoop using GNU Parallel. Who has heard of GNU Parallel before? Okay, so GNU Parallel is like a scheduler in a scheduler. So on Niagara, we have 1,500 nodes, and each node has 40 cores. So that's altogether 60,000 cores. That's great. And the trouble, not a trouble, but one of the characteristics is that whenever you schedule a job, you get a whole node. You don't get 1 core, 2 cores, 3 cores. You get 40 cores, which you're supposed to keep busy. Now, we have a parameter speed. With the 20 by 20 range, we have 400 things to do. So there's more than enough jobs for the 40 cores. That's not the issue. But we need a way to distribute those jobs to the different cores. And so that's where GNU Parallel comes in handy. We can give GNU Parallel 400 jobs to do. It lands on a single node, and it goes, I'll do the first 40. Great. Now one of them is done. It does the next one. It just keeps those 40 cores busy with the tasks that you gave them until there's nothing left to do. And so that's nice, because the alternative would be for us to script that ourselves and make sure that we take 30 of the tasks and run them, and then when those 40 are done, we take the next 40, and we have to make sure that we do load balancing. There's not one run that takes forever and then keeps a single core busy and the other ones are doing nothing. So it solves a lot of practical and efficiency issues just like that. It's actually just a Perl script. Well, I should say just a Perl. It's pretty big. It's a Perl script, so it's the scripting again, and it has a lot of features. So I'm only going to look at a few here. Another thing that's really nice about it, it actually interfaces with databases as well, if you want to. If you want to read more, here's the official publication, and there's a tutorial as well. So just to give you a first example of what this parallel command, so GNU Parallel's command is called parallel, can do. Here's a command that finds all of your CSV files and just looks for the ones that contain the word JFK. So this goes arbitrarily deep into directories. That's what the find command does. If you don't know about a find command in Linux, it's a fantastic command. It's my favorite command, find. So it finds all of your files that are called something.csv, and then I'm piping it through here to this parallel command. And what it does is it doesn't just look for the files that have JFK in it. It looks for 4 files at the same time. So the J is saying do things in parallel, 4 things at the same time. This was on my laptop where I have only 4 cores. That's why. And then each of them does grep. Grep is a search for JFK in each of the files. So there might be large files. There might be small files. The small files, you would look things up very quickly, right? So maybe there's one really large file, and if I do this 4 at a time, that one large file is being searched while the next 3 files are done, and the cores are doing nothing. GNU Parallel will take we'll see that those cores are doing nothing and give them the next files. That's the idea. On Niagara, we're going to have this be 40, but we're not going to run this command. We're going to run a slightly different command. So one thing that GNU Parallel can also do is actually give you a way to do combinatorial combinations of parameters. So here's another parallel command. It will call the command echo, which is the print command for the bash shell, for the Linux shell, and it will print. It'll take its values out of 3 sets of parameters. The first set is 1, 2. The second set is A, B, and the next set is exclamation question mark. So those triplets, triple colons just mean here comes a parameter set. But it combines them in all possible ways. So it yields 1A exclamation mark, 1A exclamation mark, then 1A question mark, then 1B exclamation mark. So all possible combinations. So it's a nice way to do parameter sweeps. We just give the parameters of the densities here, the parameters of the temperatures here, and it does all the combinations. It does the grid for us without us having to generate that. So that's nice. And then it will, so in the case of the 20 by 20, I have 20 values for the temperature, then triple colon 20 values for the density. It would make them into 400 cases. It would run them, but it would run them 40 at a time if you do -J40, and that's great. Right? We'd have to make sure that this finishes in time. Like we'd have to get, like, if we do our job properly, but that's the idea of parallel. Okay. So it actually also kind of neat way to do parameter sweeps. And then finally, and the real reason I'm putting it into a workshop on databases is that you can actually use SQLite with it. So. And it actually has this idea of having 2 steps where it first generates the parameter sets, puts them in a table, and then in the next step reads them from the table and then starts running them. But not only does it run those commands, it also keeps track of how much output they had, when they run, how long they ran, or if they run at all. So the first command, the SQL master, is the generation of this table of parameter sets. But it's a table of parameter sets plus, but it really is the table of future jobs that you're running, right? And so it creates those, and then the second one, the SQL worker, actually executes them. And as it executes them, when one is done, it doesn't just go, okay, let's do the next one. It changes the columns that correspond to how long things ran, whether it had an exit status, etc. Let me just show you. Okay, so we're creating this. Oh, wait, what happens here? Yes. So our initial one, here's the same. Oh, no, here. This is what we're doing instead. So instead of the previous case, what we're doing is we have 2 commands. We have the SQL master command. This is a little bit nasty. No, I create a list and then I join them. This is one big command. Parallel, SQL master, I create a a database called ljproject.sqlite3. That's the file. And then within that, there's a table called jobs. I give some, so I have to create jobs. These are statements or executables. So the job will, the executable is LJ. That's the first argument. Then there's a pound. The pound is just replaced by the number, or you think of it as the key. AR was for argon. And then 1, 2, 3. These are placeholders that get replaced by what follows between the colons. So the placeholders here, first placeholder is temperatures, next is density, and then number of particles, run times, time step, seeds, runtime. I could have put this in a script as well, but this is nice because I have my temperature array read in from my original statement. So I created the temperature array here, and I just feed it in here. So this has to run once to prepare my SQL job table. So I have my parameter ranges. From that follow the jobs with a certain grid. And then once that is created, and really that doesn't take too long, I create a command that will run them. So again, it's parallel. It'll do -j. Snurm task per node will be 40 when we submit to the queue, and then it's SQL worker. And again, it now just specifies the table in which the jobs are. If I wanted to be to split this up further, maybe this is too much work for a single node, I could basically do make separate tables for each and have different job tables and give them to different commands. I'm running the prepare command, so that just creates the database, and it also creates and then I'm going to create a job script. So this one has run, the table exists, the database exists. Now I want to, and that doesn't, creating that table doesn't take long, so I don't submit that to the job queue. But actually doing the simulations, that takes some time. So I want that in a job script. So it creates a job script, asks for a certain number of nodes, 40 tasks per node, because there are 40 cores, for 1 hour in this case. Give it a job name, output, sourcing the setup, and then adding the GNU parallel command. What this creates is this. So it creates 1 node, SBatch, 40 tasks, 1 hour. Give it a job name, might as well have a job name, output. And then this job sources the setup, so all the modules are loaded, and runs parallel with 40 tasks per node. It gets that from here, and takes the job specifications just from that table. Okay. It's a lot of mix of Python and SQL and other stuff here, but that's all it does. It's perfectly automated. If I change my grid, I just run this b prepare job script again. It creates a new table jobs, and what I have to do now that this is created is give this script to the scheduler with sbatch crun jobs.sh. So at least the concept makes sense. I know that there was a lot of details there. So now what does that look like? Hold on. Let's see. I can do that. So that's this b prepare jobs. So big. It creates that. Okay, it's not terribly fast, but there was a few seconds. We can deal with that. Try the SQLite again. Select star from jobs, and there we go. Not sure why it's this ugly, but anyway, that's what it created. It has also created crun jobs, and here it is. That's exactly what we had before. So I'm going to try and running this sbatch this. Oh, what did I do? You cannot submit your jobs from home. We should all know that. Okay. You should always start from scratch, but that's that was not a good idea. Okay. 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 Let's make Python A, Python B. Okay. This one should work as batch. Okay. Now it's submitted. Let's see. It's already running because it's actually a pretty short job. See how it's created all this directory. So that's the LJ program does that. It creates the directory, right? Actually gives me a. It should be done. Yeah, it is done. It's gone. Okay, so jobs, this would be everything. That's probably not a good idea. Oh. I didn't show you this one, but I can do a limit. So I can just take 2. So it has done a few things. Here's our sec element. It actually also figures out where it ran, what node. That can be useful if you're debugging or something went wrong. I think this is the time in like milliseconds or something. Let me see what was the way to get the column names again. Oh. There. Yeah, mode column. Yeah, so we have hosts, start. Oh, it's the start time. The job runtime. So this one took 3.8 seconds. How many bytes it sent to it? These are standalone jobs, so nothing gets sent or received. The exit value, if it's not 0, something went wrong. And the command that it ran. So that's kind of useful too, because the command here, where is this? Is all of this, I think. Saying it right? Yeah. So that the command is what we created initially, right? When it did the SQL master, it created those commands. If for some reason some of them would not run or have not run, it would not have start times and run times and hosts, so and it wouldn't have exit values. So they would be nulls still, and we could see which ones have and have not run. Should something not have run before, we can actually resubmit a job, and it just goes and does the ones that aren't done yet. So it's kind of nice in that sense. And at the same time, otherwise, dot exit. At the same time, we still have all of the data in these directories. In this case, it's just the output, but there we go, it's output. So this is one of the reasons why I wanted this sec thing by construction. I made sure that the directory that LJ creates is the same as the sequence number in the database. When the data doesn't live in the database, so in this case it's output on dots, how do I know which file belongs to which case, right? This is something that you have to build in. So I built that in here because the LJ command takes a first parameter, that's the directory that you're in, that you're going to put your stuff in. And I made sure when I created my my command Where is it? That magic is actually here. The first parameter to the LJ command is that pound. The pound is the number, the sec. So it creates the capital sec. SEQ is a convention that Nuperl came up with. That's why it's called that. And this one will be replaced by that number. And so now I know whenever I have a job ID, or in this case called sec 30, that is in directory 30. So I can reconstruct where my actual data is that corresponds to this job. There is no foreign key from the database into the file system. I don't have that option. So I needed to do something to make that happen. I could have also done something else where, but anyway, this was the simplest case of having, okay, a unique mapping between the run directory and the jobs table. So that's done. So now I have to collect things because yes, I have my jobs, but I don't have the output of the jobs into a table. So I would want to write a Python script that takes those, in this case, 100 jobs, and says, okay, for this parameter set, my output pressure was that, so that I could make a plot of that. So that's what the dload results does. And it's not terribly complicated, exactly because I've made sure that there is this mapping. So I'm taking, I'm connecting to the database. I'm creating a table called measurements. I added an extra keyword here, unique, which I did because what I should have done there is made this into a foreign key that links to the other sec. But apparently when I wrote this, I forgot. So this is a foreign key linking to the job, a substance, a total energy, energy. So I'm creating a measurements table here. Then I'm reading the jobs in, and all I need to read really is the command, because the command has a first argument that is the directory in which I should look for the results. So I'm reading in all of the sequence numbers and the commands from the jobs table, and then I'm looking at the command. I'm splitting it up. The command is just the command and the arguments separated by spaces. I split it up and I take number 1. That's that directory name. Okay, so don't even use the sec, but I could have used the sec. And then I add output not, because that's what I know is in. That's the name of the file I know is in there. I'm reading all of the lines in that file, but I really only want the last line. So I read the last line, and then from the last line, I'm splitting that up again, and putting sec at the end. What is, wait. Yes. So I'm appending the last line essentially to each of the arrays. So this table will be a table that is made of that last line in those elements, and that's all it does. Okay. So this again is you can't really do this within SQL, right? That this is where you need some help from Python or from R or whatever other language you want to plug your SQL into. It's just basically the data collection. But now you have your measurements table, and the table will say for which substance at which run sequence it will have which temperature and which pressure. Okay, so suppose we have that. It's in our database. Now we have several tables in there. Now suppose I wanted to do this final step where I say, yes, I want to know what the pressure is as a function of temperature and density. Or, yeah, I have another thing here from all data. So this is just a single slice. I want the lowest temperature, and now I want to see that pressure as a function of density. I could write another script, and the script would just be selecting things from the database. So I'm opening the database. I'm setting the temperature, the pressure, but they're not in the same the pressure is not in the same file as, or same table as the temperature and the density, or the temperature and density are in the jobs file, sorry, in the parameter sets file. So I have my parameter sets, P, and the pressure comes from the measurements. And so I'm going to do a join so that they can have them in one table. And then I write it. And once I have the table, I just print out the table in a nice form. So that should work too. Let's see if I can do that. So we'll load the results. I hope this works. Yeah. And extract the results. Oh, it just wrote it to screen. Anyway, it did. Okay, fine. What did it write out here? So I have a two-dimensional table in this case of temperature, density, and pressure. And so this is the full result. Okay. Okay. I did not make a plot, but that's like it's. So we put it in the file, results dots. That. Let's see if this is slower. No, it kind of looks like this. Okay. Here's the pressure, here's the temperature, here's the density. Okay. It's not particularly interesting, or so it may seem, but if you look very carefully, at some point the pressure becomes negative. So this thing does, maybe not freeze, but liquefied. So there's data in here. Good. Okay. So it is possible to combine the two, but the real value we have here, because a lot of these things, yeah, you could run those jobs and just put them in text files, is that after the fact, this thing is in a much more structured format. And I could give this database to somebody else, and they would just look at the, might not be ideal. I see things of improving it, but might figure out from those tables, oh, this is what this guy did, and did some runs, and then there were some measurements or some output, and I can kind of see how this is structured, rather than just having text files all over those 100 directories, and you go, I don't know what this is. Do always script this stuff. If this wasn't in those A, B, C, D, E scripts, then I wouldn't know next year, when I might be giving this workshop again, what I was supposed to be doing, right? For reproducibility, please script this stuff, even if, and don't do what I do, but put some comments in this. Like, I did a horrible job in that respect. Okay, so that was the use case. Now, I can see people saying, oh, I only have like 10, 20 things to do. Do I have to do this? And of course, the answer is no, you don't have to. You could keep this in your own notes, and fine. But if you're going to automate this, and you do have millions of jobs to do, this can really be useful, right? This because you come back another year later and you go, oh, I needed to do the same thing but kind of differently, finer grid, and you just dump it out. And that database, the SQL stuff, you could actually, I haven't shown this, but you could take the SQL from this database and just dump it out and put it in another database. And now you could put that data on a website, and you could do whatever with it, right? It's not just that it's nicely structured; it's also somewhat standardized, and you could take it anywhere. Okay, so summary. Let's wrap this up. You can organize data. You can do your input data, your output data. Not all data, but a lot of data can fit into RDBMS, so Relational Database Management Systems. What's nice about them is that the SQL part, and even the way that the tables are physically put in that file, you did not have to worry about it. It's just however it's implemented. So everything that I showed, you could do with a MySQL database as well, except now you have to set up a MySQL database, which is more work. The data is fairly easy to retrieve, and it's structured, so you can do queries of all kinds of complexity. You can choose your host language. We chose Python because it's fairly common and fairly easy to do. But then I abused that because Python is so easy to do to automate a whole research project, essentially, right? Now, you do have to, so there are, what was I trying to say here? I think I'm trying to say is follow those best practices when you can. Like there's a lot of ways you could just do it wrong in this one big table, or not have foreign keys like I forgot to do. That's going to bite me at some point, right? Design before you write your SQL. Try it out in SQLite 3 just to see if you've got your syntax right. Oh, and this one, this is kind of a small mock-up that we did, a 10 by 10. Make such a small mock-up. Like your workflow isn't, you're going to forget some stuff or things. Oh, I need this too. Don't do one case and then jump to the million cases, right? Do something in between just so you know that it's working. Your databases make sense. Find a machine that has a good internet or a good connection to the data center, or do it locally on your own so you can use the SQLite browser. It's much nicer than what I could show because it was sort of freezing up. So you know that everything is checked and everything is working as desired. And don't put everything in data. Raw and binary data, people don't put it in a database. There are attempts to making array-based databases, and I think they're very nice, and they might take off at some point, so you can just combine everything in one system. But those are not relational databases anymore. They are just databases plus arrays. And then it doesn't really matter that much whether you do that, or you do databases plus HDF5, or databases plus NetCDF, or databases plus FASTA. Like it doesn't matter what. The big data is not going to live in the big data that isn't transactional. It's not going to live in your database. And then I have some references. This is a class website. You should already know that one, SQLite website. Google is your friend. I haven't shown you everything about SQL, obviously. Be aware, though, there are minor but small and important SQL differences between the different implementations. So if you find something, make sure it applies to your database. Right? Look at the SQLite website first before you start Googling complex things. And one thing that I didn't mention, but if there's something, you can't do everything in SQL. But if you can do it, you should do it. So remember the where clause that we saw in the select? You could, of course, select everything, read it into a Python data frame, and then go through the data frame and check your where clause by hand. That is almost always much slower than just giving it to the database. The database doesn't do what you tell it to do. It reads that statement and figures out what the best way is to do it. So it's not going to load the whole database in and then prune it, as I said. It's going to go, OK, I have to go through the database and only pick the ones that are that satisfies that. And it does that fairly well. It's been optimized for that. And so when you can do something with SQL, don't script it in. Even if you can, and even if you're more comfortable going, I think there could be a join that works here. Just try it out. It's probably like 10 or 100 times faster than your Python loop. OK? Well, that's all I had.